In this set of videos, we're going to give a quick review of phasors and also talk about how they relate to the transmission line setting. At the end of this video, you should be able to do two things. You should be able to convert a time domain signal that is a function of z and t, and then convert it into a phasor form that is only a function of z. And furthermore, we're going to give a quick review of the concept of phasors, so you should be able to demonstrate an understanding of it by knowing what it looks like on a complex plane and be able to express it in both the traditional Cartesian form, where you just have a real plus an imaginary number, and the polar form, which is something that looks like e to the j theta. So let's start out with an overview of what a phasor actually means in the setting of transmission lines. So you'll recall from the past that we can define the transmission line equations to give any kind of wave that's of a form of f of t minus z over vp, where vp is the velocity for a forward-going wave, and something that looks similar but is of a different sign for z for a reverse wave. In this case, when we're going to do frequency analysis, we're going to start out by defining that our forward propagating wave signal is going to look like this. So recall that as long as the relationship between t and z looks like this here, you'll be okay. And we are defining this f as this cosine sinusoid here with a function of omega. Now, omega is our frequency, which is given in radians per second. You can convert that from hertz by, if f is the frequency in hertz, you can convert to radians by simply multiplying it by 2 pi. We will also later on introduce the concept of phase term beta. So this beta term we will call the phase constant. And the reason that we introduce this is so that we can rewrite this sinusoid as an amplitude times cosine, and you can multiply it in minus beta z. So this equation here is going to be our general, what we'll call the time domain sinusoid. And we're going to assume that all of the signals that we're looking at is going to be in this form. We're going to simplify everything to an individual frequency of cosine omega. Now, before we start talking about how to convert that time domain equation into phasor form, it's useful to first review Euler's identity. So Euler's identity is simply stated here, and it's much easier to see graphically. So graphically, it essentially is telling us that on the complex plane, we can express any complex number as a vector. So say the vector looks like this, with a length a at an angle theta. And what it's saying is that you can find the real part by taking a times the cosine of theta, and the imaginary part by taking a times sine theta. And this way you can see how you can convert between your more traditional Cartesian coordinate form into polar coordinate form, where, as we mentioned, if you wanted to find, if you had the polar form here and you wanted to convert it into Cartesian form, you can use these relations that we just graphically saw to find what B and C are. And if you have the Cartesian form and you're trying to find the polar form, you can see that graphically you can find A using Pythagorean's theorem, and then you can find this angle theta by taking the opposite divided by the adjacent. And taking the arctan of that. So I have this equation here. Note that this works for when the real part, so we defined earlier based on this equation here that the real part is b and the imaginary part is c. Note that this equation, here, if you just plug it straight into your calculator, it really works well for when b is greater than 0, but when b is less than 0, it might not work as well. The reason for that is if your vector was, say, over here, you would want to find this angle, which, say, we'll call phi. But when you plug it into the calculator, if you just plug in arctan of this divided by that, it's going to assume the negative sign is always associated with the numerator. So instead of giving you this angle phi here, it will actually end up giving you this angle, negative theta, because again, it assumes that the negative sign belongs to the numerator. So to adjust for that, you just need to shift it by pi. So note that in the case of conversion, you have to watch out for the fact that the calculator always assumes that when you put in a negative fraction, it's referring to something in this quadrant here, quadrant 4. And you'll have to make the adjustment to make sure it's correct. The easiest way that I see is to always draw it out and then worry about the signs later. If you see that if you have a vector that's in this quadrant or in this quadrant, you can plug it into your calculator, see if it makes sense, and if it doesn't, compared to what you drew out, you make the adjustment accordingly. Now when you do this, when you look at this, you can see that if you wanted to say, how do I get this a cosine theta? Well, you can see now that to convert the phasor form, which the polar form, which we've defined here, to what the real time domain signal we see is, the conversion is simply a cosine theta is going to be the real part of the polar form you see here. So when you just take the real part, that takes out the sign and you're left with a cosine theta. So remember, the main takeaway from this slide is that if you have something that's in the form of a sinusoid, the relationship between the sinusoid and the complex phasor notation looks like this. Now let's relate this back to our earlier time domain equation. So recall from earlier in this video, we defined a forward propagating wave v of zt to look like cosine omega t minus beta z. And similarly, for a wave that's going in the minus z direction, we have that as equal to cosine of omega t plus beta z. Now, based on our relationship that we had earlier, we saw that if we have something that's of the form a cosine theta, we got that by taking the real part of a e to the j theta. So we can actually rewrite the voltage that we see into its complex form. So for the forward propagating wave, it would look like v plus is equal to, well, v plus of zt is going to be equal to the amplitude e to the, we'll have a minus e to the j beta z here, and omega t. So notice that I switched the order of the omega t and the beta z. So switch them around for a reason that we'll talk about later. And for the negative propagating wave, you can see similarly that that is going to be equal to the amplitude e to the plus j beta z, e to the j omega t. Now the reason that I separated it out is let's just focus on what this looks like at t equals 0. So let's set t equals 0, which means that this is going to be equal to 1, and we're just left with this term here. So what does this look like on the real and complex plane? Well, it is a vector, and what's the vector length is going to be v plus. It's going to be at an angle of negative beta z. Now let's start the clock and let's see what happens as t increases to infinity from 0. What that does is this term, remember, these two terms added together form the angle, right? The angle is actually a combination of our original beta z plus omega t. So as t increases, the overall angle here is going to increase, which means that this vector here, the angle, is going to move in the positive direction, which visually means that this vector is going to start spinning counterclockwise. Not only is it going to spin counterclockwise, it's going to spin counterclockwise at a frequency omega. So it goes counterclockwise at frequency omega, and recall that omega is equal to 2 pi f, which is equal to 2 pi over t, where t is the period in seconds. So if f was 10 hertz, if f is 10 hertz, that means that this phasor is going to make a rotation of 2 pi every t seconds. So if f is 10 hertz, t is going to be 0.1 seconds. So what basically happens if in the case of f is 10 hertz is that at t equals 0, the vector starts out over here, and then after that it's going to rotate in a counterclockwise direction at a speed of 1 cycle every 0.1 seconds. So now what this also says is that if we're only interested in analyzing one frequency, let's say we're only interested in 10 hertz, then what we can do is we can actually just forget about this e to the j omega t term, because that's always going to be there and it's not going to be affected by our system as long as it's linear and time invariant. That means that the e to the j omega t term doesn't really get affected. So all you have to, the frequency isn't going to change, nothing in the time domain is really going to change. As long as you're only interested in that frequency, the only piece of information that you need is this initial phasor. So let's put it another way. What I'm saying is that in this system, no matter what happens, as time goes on, this phasor is just going to rotate at frequency omega. So in order to know what happens everywhere, all I need to know is what this starting point phasor is. Once I know the starting point in terms of the amplitude, this amplitude and this angle, then I know everything I need to know about it at any given time. I just need to add in e to the j omega t and then figure out at what time I want to evaluate. So the general steps, the phasor form of this signal here is what we have if we just forget about the e to the j omega t. So the phasor form of this plus forward propagating wave is v plus e to the minus j beta z, and for the reverse propagating wave, it's the amplitude e to the minus j beta z. So we can see that there's a two-step process to converting a time domain signal into a phasor. you can summarize it as the first step is you rewrite as an exponential. So in the case of this positive form, we rewrote it as v plus e to the j omega t e to the minus j beta z. And then step 2, we get rid of the e to the j omega t term. So all we have to do is then scratch that out, and our final answer is just simply v plus e to the minus j beta z. Let's end with a quick exercise. So we're giving you a sinusoidal voltage. It's propagating the plus z direction, so that should tell you what sign the beta z needs to be. And we've given you these characteristics here. So your mission is to convert this into a phasor form using the process that we described in the last slide, that simple two-step process. So I'll give you a few minutes to think about this. Go ahead and do it, and we'll actually solve this in the next video.